So now I'm going to look at connection between the confidence interval and the hypothesis test. So a confidence interval result will be the same as a two-sided hypothesis test result if the confidence interval level and the significance level meet the following criteria. And what is that criteria? Well, that the confidence level is equal to 1 minus the significance level. And again, remember the significance level is alpha, is a symbol used. I wish there was one for confidence level, but there isn't. So that is the relationship between confidence level and significance level. And why is that? Well, if we draw a little picture here, the confidence level is always looking in. It's the middle whatever. So the confidence level is sitting here. Okay. But the alpha level is sitting out here. As a matter of fact, like this. Notice when we were doing the finding the C critical, we always have to take the confidence level, subtract from 1, and then half it. So it turns out that if I'm doing a confidence interval, I'm looking towards the middle, but if I'm doing a hypothesis test, I'm looking out. But this edge right here is the same for both. Okay, so that means that both results will come out exactly the same. Obviously, numbers will not, but the values, I mean, the final result will be. So let's just do a quick example. You can notice again, there's no situational, just crank out some numbers. So let's just do this. I'm already have my null, have my alternative. It's a two-sided. So let's find my t value. That's 16.2 seconds. Again, you could speed me up here. I would just and what's my sample size? Oh, please give me a sample size. There we go, 22. Okay, so I would enter all that. I'm going to speed this up. I think I have some piece of paper here already done these calculations. So if I could find them, I'm just going to speed it up. I'm assuming you can do these as good as I can. I don't need to start showing you doing it. 2.3452. So I'm entering in the calculator those I have already done. And now I'm going to just start doing my process here. What's the chance that my mean? Okay, so let's draw a picture because this is important to communicate what I'm doing. So the mean is 15.1. My sample mean is 16.2. So I landed on this side. Okay. And because I'm doing a two-sided test, I need to go away from this. Okay. So that's no matter if I had landed on the other side, I would be moving away. So it's a two-sided step because it's two-sided. Wherever you land, head away from the center. Okay, so this is what I'm about to calculate. And of course, this is not the p-value. This is what I'm about to calculate, though. So what's the chance my sample mean is 16.2 or greater? And that equates to a t-score being 2.3452 or greater. And what are my degrees of freedom? So degrees of freedom for this scenario was 22 minus 1. So it's 21 degrees of freedom. So I'm going to go now to my GeoGebra, my calculator, enter my degrees of freedom. I got that, degrees of freedom, perfect. And I need to go in the right direction. I'm going greater than, select it. And now enter my t value, 2.3452. Again, notice for this distribution, I have no choice. I must enter a t value. So I'm getting 0.0145. And then, of course, that is not my p-value. Okay, my p-value is not that. So p-value will be equal to 2 times 0.0145, which is 0.029. Okay, that's my p-value. All right. Now, I was given a significance level. Ooh, look at that, how close that is. So again, I did this on purpose. Seems like all my examples today will be of nature of let's see how close we can get. So is this result significant at the 3% significance level? Yes. Our result is significant. So in fact, when I notice that we throw away the word statistically, but I'm just gonna abbreviate it. Statistically significant at the 3% significance level. Okay. And why is that? Because again, our p-value is less than our significance level. Right? So that's my p-value. And that's my significance level right there. So we have found enough evidence to reject the null hypothesis. So the result is reject null hypothesis. Great. Now let's do a corresponding confidence interval. So a corresponding confidence interval would be, okay, 16.2. Great. Plus or minus, and now I need my t critical. And again, this is based on degrees of freedom. And of course, I also need to know what should be the confidence level. So now the confidence level should be 1 minus alpha. So looks like 1 minus 0.03, 0.97. So again, this is an awkward confidence level, not one that we would choose, but I want to make a connection between the two. So really, nobody does a 97% confidence interval. And that's why I think why a lot of people just do 95%. First of all, it's pretty much what everybody use, but then the alpha levels, that's why a lot of people use 0.05 because the two are never connected if it's a two-sided test. So I got students T here. I'm going to, did I do this right last time? Yes, 22. I did change it, thank God. So my degrees of freedom here is going to be, again, 21, because we calculated already. One more thing I want to calculate is, okay, so if that's the case, what's my edge? So enter my edge. So if I'm doing 0.97, this edge is going to be 1 minus 0.97 divided by 2. So that's going to be 0.015. All right, so that's what I enter right here, 0.015. Oh, look again how close this is. Just like the other one, right? Very close. See what's going to happen here. So enter 0.015. I get 2.3278. So T star, 2.3, my critical value, T critical, 2.3278. That's what that number is. Ooh, and look at that. How close these two things are. Okay. Finally, I enter my standard error, which is going to be 2.2 seconds, square root of 22. And again, enter this into a calculator. I'm going to just speed things up here. I'm assuming you can do this as good as I can. And when I do that, I get 15.11, and here I get 17.29. Okay. And now what's happening here? Well, notice again, I'm 97% confident that my parameter is between 15.11 seconds and 17.29 seconds. Now, where is our null hypothesis? Well, our null hypothesis, remember HO was 15.1. And to make my life simple to connect is 15.10. Just even though I'm not sure, we don't do anyway. Too many significant digits. We don't do significant digits here. So this class. But notice 15 again. Here's 15.11 and then 15.10 is outside. So there's the beginning of my confidence interval, and 15.10 is outside. So notice our result will reject null hypothesis. This also rejects mu equal 15.1 seconds as one of the options for the parameter. So this rejected the null hypothesis. This will reject the null hypothesis. Let's do one more. Okay. So I'm going to construct again do this first hypothesis test. So everything is laid out. Again, notice it is a two-side, just like the other one was a two-side. This time I'm doing a 5% significance level. Okay. So let's find the T. And my average is 58.8 milligrams from a sample size of 13. Standard deviation is 4.3. Square root of 13. And when I enter this in a calculator, I get approximately this. 1.59315. And this, of course, I throw milligrams, looks like. All right, there is my result. Now we're going to go through the process. Where do we land here? Well, let me draw a picture again, just so we can understand what just happened. Our null hypothesis is 60.1. Our average is 58.8. And we landed on this side. So because, again, we're doing a two-sided test, I landed on this side. So I move away from the mean. Move away, move away, move away. So the question right now, when I'm trying to calculate it, what is this? But of course, this is not the p-value. So now I'm going to formally write this up. And now, again, my degrees of freedom. What are my degrees of freedom? Degrees of freedom is going to be sample size, 13. 13 minus 1 is 12. So I got 12 degrees of freedom here. Typically, the sample sizes for means are small, and it all really depends on your standard deviation. Remember, the margin of error, I mean, it also depends on the population standard deviation. So if the scenario doesn't have a very big standard deviation, the sample size will not have to be that big. So I got 12. I'm going to the left, so I'm going to click here, and my t-value is negative 1.59315. Hit enter, and I get 0.0686. So 0.0686. Great. That is a huge p-value. I mean, a huge probability. This is not the p-value, of course. I mean, at this point, I've already not passed, right? I haven't. This result's not statistically significant, even if I don't finish the problem. But I'm going to finish the problem because it's a two-sided test. The p-value is going to be twice this amount. Because, and remember, in a two-sided test, what we're after is, what's the chance of observing this effect size or something even larger on either side? So whatever this distance is, replicate it here. And what we're trying to do is figure out the chance of landing on either side of this or something even more extreme, if this is true. And of course, this is a huge number, 0.137. Result definitely not statistically significant at 5% level. But this really just, in general, this is not statistically significant. This p-value is much higher than even 0.1, even between 0.05 and 0.1 is, nobody uses it anyway, but this is considered very weak evidence, but this is way beyond that. So no, not statistically significant, 5%, no evidence. So this is really no evidence against null. No evidence against null. So let's go, before we do this final thing, confidence interval, let's think about no evidence against null will look like in confidence interval. If there's no evidence against null, that means that when we do our confidence interval, 60.7 better be one of the options in this confidence interval, because that would mean that this is a possibility. So remember, a confidence interval does not tell you what the parameter is. A significance test doesn't tell you what the parameter is. All significance tells you is that the thing you assume, well, continue to assume it. We found no evidence against it. Or the thing you're assuming is not correct. We found some evidence against it. A confidence interval does not tell you what is the parameter. What it does do is tell you, hey, here are a bunch of choices for the parameter. It's one of those. And that's all we get. So this one gives you a range of possibilities for the parameter. So again, using the formula, it's going to be 58, my point estimate, 58.8 plus or minus. And I'm putting here 4.3 square root of 13. And now I've got to find the t critical. So what the heck is t critical? So to do that, I need to again remind myself, what are my degrees of freedom? Degrees of freedom is 13 minus 1. Degrees of freedom is 12. So of course, that one's already set up here, 12 degrees of freedom. And I got to remind myself, what am I after? So there's a lot of things to remind yourself of. So I'm looking for 0.95. So this area is going to be 1 minus 0.95. Because why? Why am I doing that? Why am I doing this? Because my alpha level is 5%. So the corresponding confidence interval will be 1 minus 0.05. And that's going to be 0.95. Okay. So again, my corresponding is the complement. These two add up to 1. So that's why I'm doing a 95% confidence interval. And that area is 0.025. Okay. So again, I'm using this idea here. The corresponding means confidence level equals 1 minus sigma. And again, also alpha equals 1 minus confidence level if we just use a little bit of algebra to solve for one of the variables. All right, so we got this value. I'm going to come over here now and enter 0.025. And I'm doing the left side, so that gives me 2.1788. So again, notice, but that's what the plus and minus is doing, is taking into account that one of these values is positive, one of these values is negative. Because I have this direction, I just calculated the negative part. But that's what this is already taking this into account. So again, I put this in the calculator and subtract this amount. I'm assuming you can do that. And when I do that, I get the following. And notice, so again, I'm 95% confident that the mean is between this number and this number. And is my null hypothesis in there? Sure it is. 60.7 is in this, right? So somewhere in here is 60.7. So notice this confidence interval says we found no evidence against the null hypothesis. Okay. So could a confidence interval be used for a hypothesis test? The answer is yeah, it could. Sometimes statisticians will argue that there only should be, we shouldn't be going less than or greater than, we should just be doing not equal to. Of course, when we do not equal to, it's harder to reject the null hypothesis, but that's okay because when we do significance tests, we're trying to protect this whole null hypothesis. That's the whole point. This is the status quo, right? We'll choose an alternative if there's enough evidence to go against the status quo. All right, we're almost done. Now that we've done some calculations, we feel comfortable with this. Let's answer some questions and see what we've learned. All right. A two-sided hypothesis test is found to be statistically significant at the 2% significance level. Would a 98% confidence interval using the same data contain the null hypothesis? Okay, so there's a lot to unravel, but a two-sided hypothesis test, so again, two-sided, that means that we now can compare, should be able to compare if we meet the conditions. It's found to be statistically at the 2% significance level. So here's all we know. P-value, all that statement means is that P-value is less than 0.02. That is all that statement says. That's what statistically significant at 2% significance level equates to this. That's what it means. Would a 98% confidence interval using the same data contain the null hypothesis? Well, since it's two-sided, the question is, are these two complementary? And you can see they are, right? So 1 minus 0.98 equals 0.02. So the two are complements of each other. We meet the condition. So if we found the result statistically significant, it means we reject, right? We reject null. Okay, which means that if we create a confidence interval, whatever these two values are, null will not be in here. Why? Because again, that's the only way we can reject the null. We reject the null when the null is not inside this. So would a 98% confidence interval using the same data contain the null hypothesis? No, it will not contain it. Okay, no way. All right, let's look at the next question here. You are conducting a two-sided hypothesis test. Again, notice we're just going two-sided, 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 because that's the only way we can compare things. And here are some information. Mu is equal to 12.3 grams. Mu is not equal to 12.3 grams at the 5% significance level. So again, notice again how if we're about to compare, we need to be given this significance level to be able to compare. In 95% confidence interval, look, it's 5% plus 95%, 100%. So these two are complementary. Using data collected to perform the hypothesis test produces the following interval. So what's happening is we're conducting a hypothesis test at the 5% significance level. And instead of doing that, we actually created a 95% confidence interval using the data to perform the hypothesis test. And here's our interval. Using the confidence interval result only, is there evidence against the null hypothesis at the 5% significance level? And again, now because 5%, again, 1 minus 0.05 is equal to 0.95. These two are compatible. And again, because we're also doing a two-sided test, is compatible. So two things that need to happen. These two, the significance level and the confidence level, need to be complements of each other. And we need to use a two-sided test. Why? Because when we do a confidence interval is essentially a two-sided test. There's two sides to this whole thing. So again, do we reject? Well, here's our confidence interval. And the only question we get is 12.3 in this interval. Sorry. And the answer is yes. So we find no evidence against null. at the 5% level. Okay. All right. So again, this is a way to conduct a hypothesis test when it's two-sided and is create a confidence interval. Uh, as the sample size increases, is it more likely or less likely that you would find a result from a study to be statistically significant? Okay. So as the sample size increases, so n goes up, so is it more likely or less likely that you'll find the result from a study to be statistically significant? So this is a good question. And it goes back to now putting all this together, right? So one thing we do know is this. So this is this question brings some realism to this whole affair. Here's my null value. And we know that as long as my sampling process is unbiased, as n goes up, let's say we're estimating only mu, as n goes up, x bar will get closer to mu. Okay, great. Now, here's a general fact. I mean, this is just some assumed value. Maybe we found this, we calculated in the past, but we're acting as if this thing is perfect. But a lot of times that's not the case. The things we're working with that matter to us, this thing is not perfect. So what if the reality is, I'm playing a game here. What if this is what's in our null hypothesis, but the reality is that, and I'm separating, given some distance, just because so I can write this down. The reality is that this thing is the correct value, but we just don't know, right? So as n goes up, x bar will get closer to, well, the real whatever it happens to be. So at some point, if n goes up, this thing, as we've seen, now I'm creating a little confidence, this thing will get tight and not include this little fellow. So eventually it will price this guy out. If, again, these are very close to each other, but again, if n gets large enough, all of a sudden, I'm not including this potential value. And these two are really insignificant. Let's say, the difference here, we care less about. One number is as good as the other. But again, eventually that means that if that's really the reality we're dealing with, yes, as sample size increases, it's more likely you'll find result to be study to be statistically significant. Yeah, it potentially that is true, even if this thing is correct. Obviously, if it's not correct, like let's say now this thing is not correct and this is correct, and they're far apart, then yes, as the sample size increases, it is most likely that you will find the result to be statistical. So in either scenario, even when these two things are not that close, then yes, that's absolutely true. And even if these two things are close, and this is of no practical importance, you will still reject eventually. So this is why it's important to kind of determine the effect size, okay, between this and this, to see if the difference is something we care anything about. After all, we will still not know what this value is. We just don't know what it is. All right. A result is found to be statistically significant, but it is of no practical importance. What does that statement indicate? Again, it means we found evidence against the null, but the difference, and there's different ways of stating this. This is not the only way, but I'm trying to make this as simple as possible and not introduce anything else that we know. But the difference between the null value and our statistic let's say, for example, X bar. Yes, and what am I trying to, so sorry, the difference, but the difference between, sorry, I have to interject this here, but the difference between mu, the null value, and our statistic X bar is of no practical significance. I mean, I'm starting to be using the same. I guess I won't do that. Is maybe I'll try something else. Does not matter for practical purposes. Okay, so that's all that means. And you can, I'm going to put some links here of other people trying to explain this idea, and they're all going to pretty much say the same thing. Give you some more better examples, maybe some clinical examples. A 1999 study looked at large sample of women aged 20 to 24 years of age, over 50,000, to estimate the mean total cholesterol level among women. The results were a mean of 168 milligrams per deciliter with a standard deviation. So I'm looking at total cholesterol among women in this age group, were a mean of 168 milligrams with a standard deviation of 27 milligrams. Okay, so okay. Again, it's a good large study. I mean, this is like 50,000 people. Okay, great. Another study wanted to see if there's a difference in the mean cholesterol level of women that are considered sedentary in the same age group. Okay, so in the same 2020, but women that consider sedentary. So now they tested 10,000. And this study found the result to be significant at the 2% significance level. So they did 10,000. So it's a very large sample size. Notice my standard deviation is very tiny. So what did it find? It was definitely significant at 2% significance level. So alpha was definitely low, my p-value is less than 0.02. But the mean cholesterol level, the difference between this number and this number, so notice the difference between these two numbers is not that great. Okay, so 168.6 minus 168, so 0.0, not 0.6 milligrams per deciliter. Now the question becomes, okay, we found the result to be statistically significant, but is that important? Is it different? Like, okay, is there a difference? So this question is there a difference between the two groups? The answer is yes. So we found the evidence that there is a difference between the two groups. Okay, but the question is, okay, how big is that difference? It turns out not that big. And of course, these are just two estimates. If we did a confidence interval, we would get a better idea. And maybe these two wouldn't overlap by much. But the question is this really important? Like, do we care about it? Should we be alarmed? Well, I'm going to stop the video for a second and look something up real fast. So I looked at some website, Cleveland Clinic, and pretty much everything else seems to suggest that this is correct. But this had a nice, cute graphic. But looked like we were looking at total cholesterol level, and I'm looking at now different, obviously broken down between the two different types of cholesterol. But looks like, hey, heart healthy, under 200, fine. So it turns out that maybe the women in this age group, 2024, a cholesterol of 168. Well, shoot, that's great. Under 168, total healthy heart. What about those sedentary women in that same age group? Well, slightly higher, but guess what? They're still they're a healthy heart too. So while there might be a difference, who cares? There's not anything important here. So that's the difference between statistically significant. Yes, there's a difference between the groups, but is there a practical importance to this difference? And the answer is no.